Hey, welcome to Secants and Tangents, whatever that means. And I've got a burning question for you here, a red hot question. When is a chord not a chord? And first of all, what is a chord? Oh, there's one over there. When is a chord not a chord? When it's seeking to be something bigger. Well, do you know anything about secants? Well, here's a secant here. A chord is a line segment joining 2 points on the circumference of a circle there, or on a curve. Here we're talking about circles. And a secant is the line through those 2 points, cutting the circle. It keeps going. So there's the difference when a chord wants to be bigger, when it wants to keep going in both directions. So it comes from the Latin. So this is a secant when it's that line, and it comes from the Latin meaning to cut. Secare, I think it is the origin of that word, secant. So it's a chord which cuts through the circle, doesn't stop at the 2 points there. Okay, so that's the idea. Excuse me, got a bit of a cold here. That's the idea, and what we're going to do is look at special properties of these secants. And of course, a tangent is a line that just touches the circle, like that one. I think you know these other words, radius and diameter, but there are some special theorems now that we can use in deductive geometry that are related to secants and tangents. So come on down and let's have a look at the tangent stuff, because here's another question. What is the limiting position of a secant? Limiting position. Well, there's a secant. It cuts the circle in 2 places, here and here. And if I move this around, I could make another secant through, well, that's not very good, that one. Let's just try and get rid of that. Another secant through this same point, down here, but a different one. If I kept going around here, can you see the limiting position would be, as this point approaches this other one, the limiting position would be tangency, wouldn't it? And you'll do a bit of this in an area of mathematics called differential calculus. Limiting position of a chord or a secant is tangency. As you come closer around the curve of one point to another. So it actually, if you like, falls off the curve, only cuts at one point, or touches at actually one point, and so you've got a tangent situation. So some interesting things here, the relationship of these lines and line segments to each other. What we're going to do, though, is to have a look at the theorems or rules connecting these things and see how they can help us with deductive geometry. So come down now, and we'll just get rid of that, and see what we've got for you. Here we are. So here's the definition. A secant of a circle is a line that intersects a circle twice. A chord is a line segment. That's the difference, which connects the points of intersection of the secant. So a chord would like to grow up into a big secant. At the moment, it's only a line segment. Okay, come on down, let's look at the theorems, and they're rather interesting. The intersecting chords theorem. If chords AB, let's have a look, AB joining 2 points on the circumference, and CD intersect at X, yep, see that, then AX times XB equals CX times DX. Oh, how would you get a multiplication out of a deductive situation? How could you deduce that? Well, I think it's going to be pretty obvious in a minute that first of all, we've got a lot of stuff to do with cyclic quadrilaterals, haven't we? And ABCD coming down here is a cyclic quadrilateral, because A and B are points on the circumference, and so are C and D. All right, so now in that we've got alpha 1 equals alpha 2, subtended by the same arc, beta 1 equals beta 2. We've got vertically opposite here, if we want to put that. So we've got equiangular and similar triangles there, AXD and CXB. Okay, AXD and CXB. And you know with similar triangles that the ratio of corresponding sides is the same. So AX to CX is DX to BX. And of course, if we multiply both sides by BX and then CX, you get the required product. Rather neat, isn't it? It was always sitting there as a result of this common ratio idea, but didn't ever spot it. So there's an interesting little result. And that can be quite useful in working with some of these figures. Okay, so that's called the intersecting chords theorem. When we've got two chords intersecting, those two products are equal. Now, how are you going to remember it? It's AX times XB, CX times XD. So take one end of a chord, go to where it intersects, multiply by the other end, and that must be the constant value for any pair there of intersecting chords. Okay, we'll use that one a bit later on. Okay, come down, let's have a look at the other two, the secant tangent theorem and the secant theorem. And they're all to do with lengths. So we've got a tangent here to a circle, meets the chord VA produced at X. So the chord, remember, is a line segment. It stops at points on the circumference. If we produce it out to X, it's going to intersect that tangent. Now what we can say here is that the square of that equals the product of XA times XB. Just watch that product though. It comes from the point of intersection of the tangent with the extension of the chord, and here it goes XA to the first point of the chord and times XB, and that equals XT squared. So it's another length result. And I don't know, but there's a square in there. Would Pythagoras have something to do with the proof there? Now, we're not going to prove this one right now. We're going to put that as part of an exercise for you later on down here. And just noting here that the screen clippings here from Hayes and Harris Publications with the new SACE Year 11 pre-specialist textbook here. Okay, what about the secant theorem? Okay, so we've got two secants here, and X is outside, and it's a point of intersection of the secants. So this time, XA times XB equals XC times XD. So that's a secant theorem. The secants have to be extended so they intersect, and then if they do, we have this little interesting product of their lengths. And one would perhaps guess that you would use similar triangles again to try and do this one. Again, we're not going to do the proof here. It's part of your exercises later on as you get to use these. So come down. Let's have a look. There's some interesting converses here. So if you had A, B and C, D meeting, so what are A, B and C, D? A, B and C, D meeting, and if you could show that AX times BX, so that's this product, equals CX times DX, then you could say, AC and BD would be chords, or ABCD would lie on the circumference of a circle, because this is the intersecting chord theorem. AB and CB and CD are chords, and we know that's a result. So this is the converse, going backwards. So that's a final way of showing that something is cyclic, using a converse or reverse of the intersecting chord theorem. And here's another one, of course, proving with the other tangent secant theorem that something is a tangent. Okay, so here, if you've got 2 points on a circle, so let's look at this one. So 2 points on a circle, not a very good circle there, Huddy. 2 points on a circle, and we're going to say now something like this. And X is a point, so there's collinear, so we extend this out here to X, and there's a point on the circle such that XT, so we go here, so that XT squared equals XB times XA, then that's a tangent. So that's interesting, a way of proving tangency without calculus. Okay, so that's an interesting result. So both of these converses could be quite useful in working with cyclic quadrilaterals or circles in general. All right, are you ready to have a go? Let's have a look at some examples from Hayes and Harris here. Find x in each of these. So we notice these 4 points are on the circumference, so there are 2 chords there. Line joining that point and that point, 1 chord, that point and that point, another one. So it's the intersecting chords theorem. We can say here that x times 5 equals 3 times 4. And so 5x equals 12, x equals 2.4. Intersecting chords theorem. So I would put that in brackets after that rather than writing sentences. That's the way we usually do deductive geometry. Now this one here in part B, we've got 2 secants and they're continued on to a point of intersection. So the intersecting secants theorem is that 4 by its whole length, 4 plus x, is equal to 5 by 5 plus 7. Okay, so x is 11. Again, it's preferable to put that reason in brackets after your deduction. Okay, what about this one? There's a secant and there's a tangent. Can you find x? Well, by the secant tangent theorem, the square of the length of the tangent equals the product of the parts of the secant. So here it's 2 by 7. Remember, it's the whole chord there. Not chord, whole length of the secant to the point of intersection of the tangent. So it's this first bit, 2 by the whole length. And again, putting that reason in brackets, I think, is a good idea. All right, and of course, this is important here, mathematically. X squared is 14, x is root 14, as x is greater than 0. You're being very cognizant of the fact that a squared equation, x squared equals 14, has 2 solutions. X is root 14 or x is neg root 14. And you're saying, we know that, but we're choosing root 14, the positive root, because it must be a length and it must be positive. So please put something there. Sometimes books put both solutions and then just this one with the answer, with the reasoning x must be greater than 0. So you can omit this, but you must put this because the mathematics saying that x squared equals 14 means x equals root 14 alone is wrong, because the squared equation has 2 solutions and you've chosen one and you must put that. Okay, come down, your turn. And I haven't put all the solutions to these, I've just taken them from the back of Hayes' book there with their hints. So hopefully you'll be able to work with your teacher or other students to work out how this all works out. The theorem is okay for the first couple. Excuse me. And then we might have to use a little bit of similar triangles and stuff here for a later one. Here we are. Use the angle between the tangent and chord theorem to prove the secant tangent theorem. Okay, so you can have a go at that one using the same ideas as before with the intersecting chords and so on, some of those. So pause it and then go and have a look at the answer. Here's the secant theorem. Use the opposite angles of cyclic quadrilateral theorem and similar triangles to prove the secant. That's an interesting one. And number 11's in red, could be a bit challenging, that one. All right, have a go, and I'll show you the answers now and the hints. Haven't got all the proofs there, but some of the hints of construction and ideas that you might use to prove those things. All right. Well, that brings us to the end of the pre-specialist geometry for Year 11 leading into Year 12. So I'd suggest you go back over all the work and all the theorems, write them out. It's best if you can memorise them so that they're right close to you when you need them. For the moment now, it's cheers for me. Catch you a bit later.